Assalamualaikum. We are from group 2 from section 3 for BFC 43003, which is steel and timber structure design. The project is about propose a design for one-story frame. The calculation of work design must be provided as follow. First is truss, second is column, while the connection is both joint in truss, and the second one is truss to column. Decision on project building. Our group is responsible to propose the design of one-story frame, which is school canteen in UTHM. The location of the construction is planned to be in area which is suburban area with flat topography, with less than slope less than 0.05 and dense terrain. This is frame geometry. First is proposed roof design. Second, plan view, side elevation, and lastly front elevation. For structural layout, which is bottom chord, top chord, purlin, and vertical brace for the design.
Hi, my name is Layongi and I would like to present the loading part. In this project, there are two basic load on trusses needed to be considered for the design. The first one is the permanent action, including the roof covering, surface of the trusses and fueling. The second one is the variable action. For the roof, the action are summarized as follows. For maintenance and repairing purpose, the variable action is equal to 0.75 kN per meter square, and for other purpose is equal to 1.50 kN per meter square. In our project, we use the aluminum corrugated roofing sheet. The GK is equal to 0.048 kN per meter square. The surface of the trusses is equal to 0.10 kN per meter square, and the surface of the purlin is equal to 0.03 kN per meter square. So the total permanent action GK is equal to 0.178 kN per meter square, which is on the slope. For the variable action, we take the roof for purpose of maintenance and reparation only. So we multiply the 0.75 by this value to convert it on the slope. Then we get the QK is equal to 0.784 kN per meter square. For design load per unit area, we use the equation 1.35 GK plus 1.5 QK. Then we get the W is equal to 1.362 kN per meter square. The point load on the node P, we multiply the W by the spacing of truss and the spacing of purlin. Then we get the P value is equal to 6.34 kN, and the P for both end sides divided by 2 is equal to 3.17 kN. This is the load distribution for the side view of our project, and this is the plan view of our project.
Hello, my name is Muhammad Nasrul Razali. AF 160031 will present about trust. Introduction. Trust is an arrangement of bar or member connected at joint, welding or bolting, only tension or compression and no bending. The members are connected with a gusset joint that is either riveted, bolted or welded. Only axial force are induced in the structure. The truss can be two types, which is planar truss or space truss. Planar truss is a member line in a two-dimensional plane. Space truss is a truss line in three dimensions. Three basic parts of truss. One is a top chord. Top chord is the beam at the top, which is usually in compression. For the bottom chord, beam at the bottom, which is usually in tension. Where are interior beams. Next is three basic load on truss. Permanent action, which is cladding, insulation, sealing, self weight of truss and purlin. Next is variable action, which is 0.75 kN per meter square for only access to the roof for maintenance and repair. 1.5 km per meter square where there is access in addition to that roof. And the last one is wind action, need to follow the guideline by the Eurocode. Next is for combination of load. The four combination of load is dead load, alone, dead load plus imposed load, dead load plus imposed load plus wind load, and dead load plus wind load. This is the design truss procedure. First is start. Next is loading. After we get the loading, we analyze, assuming all joints are pin jointed and all loading nodes. Therefore, the output will be first, tensile stress normally occur at bottom chord and slope internal member. 2. Compressive stress occur at top chord and the vertical internal member. Next, analyze of the load-bearing members such as rafter as a continuous pin supported at node and loaded by the purlin. If the load position are uncertain, the rafter moment may be taken as Ws²/6, where L is the nodes to nodes length of the rafter and W is the total load per minute unit length applied perpendicular to the rafter. Assessment of stress due to eccentricity of the connection. Assessment of the effect of joint rigidity and deflection. And okay, next is I will talk about design of purlin. Purlin is normally placed perpendicular to the rafter, and set rope may be added to the reduced bending moment of purlin. Based on Eurocode, purlin must satisfy regarding to the slope of roof should be less than 30 degrees from horizontal. Loading on purlin should be uniformly distributed. Limitation of section of modulus Z about its axis, member dimension D and B are given in the table 2.7 in the Eurocode. Next, this is the example of the table 2.7 that we refer to calculate the purlin. Minimum steel grade for the purlin is S23775. Unaffected load should be used. For our project, the spacing between truss we calculate is 6.1 meter. Spacing between purlin is 0.765 meter. Our GK and QK is 0.178 kN per meter square and 0.748 kN per meter square. According to the BS, the roof slope should be less than 30 degrees. So we calculate our roof slope using tangent theta. Our group get 4.12 degree, which is less than 30 degrees. For our WP, 1.0 GK plus 1.0 QK, we get 1.05 kN. For the table 2.7, we use the formula WPL over 1800. So we got our group got the ZP is 3.56 centimeter cube. For the D, the formula is L over 45. For our group, our length is 6,100 millimeter, and we divide by 45, so we get 135.56 millimeter. For B, our group get 50.83 millimeter, and the total permanent load and total variable load, which is 0.691 kN and 3.499 kN. And the design load is 1.35 GK plus 1.5 QK, we got 6.18 kN. So the moment that we calculate, we get 0.60 kN. This is our load distribution, the sketch of the load distribution. Next is we calculate the MCRD. For the MCRD, we use the formula WL mean Fy divided by M0. WL mean we get 2.18 centimeter cube. Therefore, we use a single angle 45 times 45 times 5L, which is 2.20 centimeter cube. After that, we need to calculate the deflection. The deflection for our design is 90.70 millimeter. For the allowable deflection is 30.5 millimeter. So our deflection is okay. That's all. Thank you.
For the bottom chord, for the tension design, which we got FY235 and ED250. Therefore, we assume the both sides that we use are equal to 20 millimeter. The B2 that we got is 0.70, and net we got 750 mm squared. Therefore, the NURD that we calculate is 140.4, MPLRD 225.6, NTRD 290.2. To verify, we got the value is 0.86, which is lower than 10. Therefore, our design is okay. Then, for the compression member, the member are subjected to compression load, and ED equal to 1630 kN. For withdrawal section 244 times 10 CHS, and the diameter is 244.5. T10 area 6370. Then for the section classification,
Hi, I'm Danny Mu Ming Huang. I will present you about the design of column. Column is a structural member which is subjected to compression. Columns are designed to carry axial load and prone to buckling failure due to their strengthened nature. In real life, columns are not only subjected to pure compression but also bending. When an eccentric axial force is loaded on the column, bending moment will occur due to eccentricity of the load on the column. For the column design procedure, step 1, we will analyze the steel structure using step pro to determine the axial load and ED. Step 2, we will select the section based on the area of the section calculated using the formula as below, which is NED equals to A Fy gamma M naught. From the formula, we will find out the area, which is by multiplying NED with gamma M naught divided by Fy. For the area of section calculated, we can determine the type, grade, and area of section that is suitable to be designed for the column. For the step 3, we will carry out cross-section classification of the section to eliminate local buckling. For the step 4, we will calculate the slenderness ratio of the steel. Slenderness ratio, which is greater than 0.2, is considered as slender column, and we will design it as slender column, and buckling resistance checking is required. However, for slenderness ratio less than 0.2, we will design it as a stocky column where buckling resistance check is not required. For the step 5, we will proceed with the cross-section resistance checking, where it will check and verify using the formula as below, which is NED over NCRD less than or equal than 1.0. For step 6, buckling resistance checking of column. First, we will determine the alpha by determining the required buckling curve from table 6.1. Second, we will calculate the phi by substituting in the value of alpha and lambda. However, we will calculate the chi by substituting in the value of phi and lambda. For the fourth, we will determine the design buckling resistance of the member of the column, and we also check and verify the buckling resistance of the steel using the formula as below, which is NED over MBRD less than or equals to 1.0. This is the figure of the reactions that we obtain from the step 4. As you can see, the maximum and critical collar lock is equal to 42.347 kN. So we will take it as an NED to design for our column. The determination of the critical axial load. We will try, this is the area we calculated using the NED, so we'll get area equals to 1.54 centimeters square. So we'll try the section 152 times 152 times 23 UC to design as the column of the structure. For the cross-section resistance, we will get NED over NCRD is equals to 0.053, which is less than 1.0. So it is sufficient. For the buckling resistance in y-axis, NED over MBRDY will be equals to 0.06, which is also less than 1.0, and it is sufficient for the column. However, for the NED, for the x-axis, the NED over MBRDX is equals to 0.08, which is also less than 1.0, and it is sufficient to resist the bending. Hence, 152, 152, and 23 UC grade S275 is suitable to be designed as the column of the steel structure.
Hi, I'm Senzong, and I present about the truss to column using the bolt connections. So the bolt connection of the truss to column is designed in the single shear planes. Then we use the bolt class, which is the grade 4.6. Then we get FYB 240 and the FUB equal to 400 Newton per millimeter square. Then the diameter of the bolt we use is 20 millimeter, and then we get A equal to 314 millimeter square and S equal to 245 millimeter square. For the checking for single shear plane, we will first check for the shear resistance, and it is assumed that the shear plane passes through the threaded portion of the board. Then first calculated the shear resistance per board FBRD using this formula. Then we get 47 kilonewtons. For the load due to the shear, we're using this formula FBED equal to P over N. We get 7.06 kilonewtons, which is less than or equal to FBRD that we calculated before, which is equal to 47 kilonewtons. Then it's okay. For the bearing resistance per board is BRD equal to this formula, and for M boards we have calculated AB equal to 0.606 and the inner board AB equal to 0.659. Therefore, for the M boards FBRD we calculated, we get 159 kilonewtons. For the inner board we get 172.9 kilonewtons. Then we compare with the FBED. FBED equal to 240 Newton per millimeter square multiplied by the B 20 multiplied by 16T. Then we calculated that 76.8 kilonewtons, which is less than or equal to FBRD, equal to 172.9 kilonewtons. Therefore, it's okay. For the tensions, it is assumed that the board is not the countersunk board. Then we get K2 equal to 0.9. We substitute it into FTRD, K2 FUB AS over gamma M2. Then we get 88.2 kilonewtons. For the FTED, we calculated using this formula PY1 over 2 summation of Y square. Then we get 12.70 kilonewtons, which is less than or equal to FTRD that we have calculated before, which is 88.2 kilonewtons. Then it's okay. For the combined shear and tensions, we calculated using this formula. Then we get FBED, we calculated FBRD, FTED 1.4, FTRD. Then we get 0.297, which is less than or equal to 1. So it's okay. That's all from me. Thank you.
Okay, now we move to the conclusion. In this part, we know from the report there may be several errors that obtained from the calculating of the design load acting on the structure. By the way, we managed to cooperate as a team conducting and increase our knowledge in the manual calculating and software relating the steel structure design. In our recommendation are we making the research on loading acting on the actual structure design and make comparison with the proper design structure. For the second one, we comparing the software result in the StatPro software or Esteem software with manual calculation to obtain the most stable result and stability of the structure. And the last one, referring to the lecturer, which is our lecturer, Dr. Hilton, to know the step and method of applying the formula according to the Eurocode 3 correctly. Therefore, we summarize that the structure proposed is stable under suitable for arrangement and loading for the structure system based on the manual and calculation.